Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about one more example of the mean of the output y of t and the power spectral density of the output y of t. This is the previous examination question. The example is the input voltage to an RLC series circuit is a stationary random process x of t with expectation of x of t is 2 and autocorrelation function of x of t is 4 plus e power minus 2 mod t. Let y of t be the voltage across capacitor, Find expectation of y of t and power spectral density of the output y of t. Coming to the solution, so given that consider and a series RLC circuit as shown in this figure. Let I of t be the current flowing through the circuit. So applying KVL equation to this series RLC circuit. So Ri of t into Ri of t plus L di of t by dt plus 1 by C integral I of t dt is equal to x of t. So in this equation, taking Fourier transform on both sides, we get R is the constant. Fourier transform of I of t is I of omega. L is the constant. Fourier transform of di of t by dt is j omega into I of omega plus 1 by c is constant. Fourier transform of integral I dt is I of omega by j omega is equal. Fourier transform of x of t is x of omega. So the voltage across the capacitor, the series RLC circuit, the voltage across the capacitor value is y of t is equal 1 by c integral I of t dt. In this equation, taking Fourier transform on both sides, Fourier transform of y of t is y of omega, 1 by c is constant, Fourier transform of integral I of t dt is 1 by j omega into I of omega. So the system function or the transfer function h of omega is equal output by input, that is y of omega by x of omega. Now here y of omega value is I of omega by j omega c and x of omega value is r I of omega plus L j omega I of omega plus 1 by c into I of omega by j omega, and substitute those two values into the system function equation. This is the expression. So now here in the denominator term, take the common I of omega, and after taking the denominator I of omega, numerator and denominator I of omega is cancelled, and in the denominator term take the common 1 by j omega c also. We get h of omega is equal 1 by j omega c. In the denominator term take the common 1 by j omega c into j omega cr plus j omega L into j omega c plus 1. So numerator and denominator 1 by j omega c is the cancel, and the remaining term is 1 by 1 minus omega square LC. So j omega into j omega, j square value is minus 1. So 1 minus omega square LC plus j omega CR. So this is the system function expression of the RLC series RLC circuit. So now taking magnitude on both sides, magnitude of h of omega is equal 1 divided by square root of real part square plus imaginary part square, that is 1 by square root of 1 minus omega square LC whole square plus omega CR whole square. So taking squaring on both sides, magnitude of h of omega whole square is equal. On RHS side, square and magnitude is cancelled. Square and square root is cancelled. We get the remaining RHS term is 1 divided by 1 minus omega square LC whole square plus omega CR whole square. The power spectral density of the output y of t is Syy of omega is equal magnitude of h of omega whole square into Sxx of omega. So now here magnitude of h of omega whole square value is calculated. So given that the autocorrelation function is Rxx of tau is equal 4 plus e power minus 2 mod tau. So given that the autocorrelation function of x of t is 4 plus e power minus 2 mod tau. So taking Fourier transform on both sides of given autocorrelation function, Fourier transform of Rxx of tau is equal to Fourier transform of 4 plus e power minus 2 mod tau. So Fourier transform of autocorrelation function is power spectral density, that is Sxx of omega is equal 4 into Fourier transform of constant function is 2 pi del of omega, plus we know that Fourier transform of e power minus a mod t is Fourier transform of e power minus a mod t is 2a by a square plus omega square. So Fourier transform of e power minus 2 mod tau is 2. Now here a is 2. 2 into 2 by 2 square plus omega square. So therefore Sxx of omega is equal 8 pi del of omega plus 4 by 4 plus omega square. So therefore now here substitute Sxx of omega value and magnitude of h of omega square value into power spectral density of the output y of t equation. Therefore, the power spectral density of output y of t is Syy of omega is equal magnitude of h of omega whole square value is 1 by 1 minus omega square Lc whole square plus omega cr whole square into Sxx of omega value is 8 pi del of omega plus 4 by 4 plus omega square. Given that the mean value of x of t is 2, so find out the mean value of the output y of t, that is expectation of y of t is equal h of 0 into expectation of x of t. So h of 0 value is 0 frequency response of the system value is 1. So now your expectation of x of t is 2. Therefore, the mean value of the output y of t is 2.